All right, so this lesson is about the central limit theorem. So I'm just going to do a fair warning up front. There is a lot of buildup to actually get to what we're talking about. All right, but I promise this is going to be the most simple thing we have done all semester. As long as you understand the 7.1, 7.2 sections, this is going to be easy peasy. But it's a lot of stuff up until that point, up until I tell you this is why we're doing it. It's just one little thing, literally just one small thing that we're doing for this lesson. But I do need to explain some of the stuff of why we're doing it and what's happening here, all that kind of stuff. But if you hold on with me, right? I promise this will end up being one of the easiest things we've done all semester, so long as you understand that previous sections that we've already talked about. All right, because it's just a little different than from those sections. So let's talk about a sampling distribution. So if you notice in section 7.1, 7.2, right, these are all about normal distributions. And it was a normal distribution of a single person, right? So a lot of the questions would say something like, if we randomly select a person, right? If a thing is randomly selected. But what if we have a sample of people, right? What if there is some sample, 10 people, right? What if we randomly select 10 different people to do something, or 20 different people, right? So a sampling distribution will be a probability distribution for all possible values of your sample size, whatever n is. A sampling distribution for a sample mean, right, is also a probability distribution of all the possible values from your sample size from a population with a mean. So if it's population mean, that's mu, or standard deviation. If it's a population standard deviation, remember that's sigma. Okay, so basically, we want to know if we can do a normal distribution, right? We want to be able to do things in our calculator. So if it gives you stuff and it says you want to be able to do either normal CDF or inverse norm, right? So this is what we want to do. We want to be able to use inverse norm or normal CDF essentially, right? We want to know that we are dealing with a normal distribution. Well, how can we know that we're dealing with a normal distribution? Well, one is super easy. The population tells you it's normal, right? It just says that the population is a normal distribution. Perfect. Awesome. Super easy. However, there is a second one. If the population is not normal, is there something that we can do to get a normal distribution, especially if we're trying to figure out for a sample size, right? So here's some examples. Here is our one example. So if we're doing a die cast, right? So think about a regular die, right? Six-sided die. Let's make a probability distribution about that looks like it. So probability distribution, remember x is the random variable. P of x is the probability of each of these things. So random variable, that means the probability, or that means an outcome, right? The numerical outcome. So what are the outcomes if you roll a die? You get a 1, you get a 2, 3, 4, 5, or 6, right? For the probability of all of these things. So what's the probability of getting a 1? Well, hopefully we see that's just 1 out of 6, right? What's the probability of getting a 2? So some of y'all might have been quick to say, oh, that's just 2 out of 6. But that's not quite true, right? If we think about it, there's 6 sides. How many of them has the number 2 on it? Just 1, right? One of the sides has a 2, so this is also 1 out of 6, right? And actually, it should be 1 out of 6 for all of these. So if we were to graph our chart, we would see that we would have what kind of distribution? Is this a normal distribution? Definitely not, right? This is a uniform distribution. Wow, I am losing my mind for a second. Uniform distribution. There we go. right? So, can we do normal CDF with these types of problems? No, not as of right now, right? Because the population is not normal, it's uniform. Okay, so if we're trying to find the mean of a bunch of samples, so let's actually do this, right? So we're going to do this 9 different times, right? And so what we're going to do is we're going to roll 4 die and take the sample mean of it. So let's say, so what we can do is we can say a random between. So basically, it's going to pick a random number between 1 and 6, which is basically like rolling a die, right? So it rolled the number 6. We're going to do that 3 more times. So now, right, when it rolled the die 4 different times, right, we got 4 different numbers. And so we're going to take the average of all of those, right? So add them up. Oops. Divide by 4. And there we go. So we're going to do that 9 more times, right? So essentially you can think about, and you can actually do this at home too, if you'd like. You can actually just find a die and roll it 4 different times and then take the average. 4 times, take the average. 4 times, take the average. Right? All right. So we've taken all of these and we've taken the average. Now, what I want to do is let's take the average. Well, nope, I lied. Let's not do that yet. So what we're going to do instead is we're going to make a new distribution, but this time, this time our x is going to be the sample, and we're going to write the number of them. Right? So on this side, right, I actually already did this. So we're going to have 1 to 1.99, 2 to 2.99, 3 to 3.99, 4 to 4.99, 5 to, we could say 5.99, but 6 is close enough, right? So we can just do that. So what we're going to do is we're going to count the number in the sample mean, right? Because if you remember from the very beginning, we said that this was a sampling distribution of the sample mean. So how many numbers do we have? So we can just count them up. We can also, and I already did it, so we can just do that. Cool. So what we can do, we can actually take this graph, right? So what kind of graph do we have here? Well, this is definitely not normal, right? This is not a normal distribution. So can we do normal CDF and inverse norm? No, we cannot. Okay. Well, maybe the sample size was too small. Maybe 9 is not a big enough sample size, right? Let's try 50. So if you notice what I did here was I actually did it the exact same way, right? We just did it 50 times. So when we do the exact same thing, right? We take our sample size, and what I did was I counted essentially, or I let the Excel sheet count how many are between here, right? If you really want to, you can pause the video and count how many are in between here, right? Make sure it's the same as mine. And so what we can do is, hold on a second. We can make a distribution. Oh, look, we finally have a normal distribution. Well, that's kind of cool. So normal distribution, right? Still relatively normal. Good. All right, but the population is uniform, right? So what's happening here? Well, if you notice, right, the more averages that you take, right, over and over and over again, well, the more likely you'll have things in the middle, right? which makes sense. So basically, so this one ended up being normal, right? That one, it's still kind of normal. Ooh, definitely not normal. Definitely not normal. Definitely not normal, right? So let's see with this one. How many times does this one end up being normal? Still pretty normal. Still pretty normal. Ooh, definitely not. Not really. Maybe. Kinda. Yeah, that is. Okay. So it seems like this might have been one time it wasn't normal, whereas here it was a few times it's not normal. Still not normal. Ooh, definitely not normal. Definitely not normal. All right. So it does look like at some point there's a cutoff to where the number of times you do this, right, over and over and over again, you end up getting a relatively normal or approximately normal thing. And what we end up seeing is that when your sample size so what we had, so we said 9, probably not great. Ooh, yeah, no, that's awful, right? Definitely not normal. 50, yeah, we only had like one that wasn't relatively normal. All of them are, I mean, that's, ooh, no, that's not. Kinda, not really. I'm just going to stop while I'm ahead. 50 works. So the question is, what's the cutoff point for our sample size, right? We actually did this 50 different times, right? So the question is, what would be the cutoff point? So when our sample size is greater than or equal to 30, we can assume that it is approximately going to be normal. Right? So just like what we said, when we're taking averages, right? If you have at least 30, you're going to have an about normal distribution. Less than 30, probably not. Well, maybe, but more than likely not. Yeah. Cool. And this works for anything, right? Because again, it started off as a normal distribution. As a uniform distribution. So, when we have a normal, when we have a simple random sample of size n, and it comes from a population with a mean of mu and a standard deviation of sigma, then as we already said, so we can do this so long as the population is normally distributed or the sample size is greater than or equal to 30. So we can basically assume that we get a normal distribution or approximately normal, which means we can do normal CDF. So if you know the population is normal or the sample size is greater than or equal to 30, you can do normal CDF or inverse norm in our calculator. Those are allowed. All right, so let's talk about what this symbol means right here. So basically what this means is if you notice, this is a mean, a population mean. This is sample mean. So what this means, it is the mean of the means, right? Of the sample means. So if we go back into our example, if we take the mean of all of these sample means, what we end up with is 3.57. Now, let's take the average of our actual distribution, right? So the original distribution, our sample distribution. So in your calculator, what you can do is you can do L1 and L2, right? So this is from section 6.1. So we plug in all of our stuff here, 1/6 there. So we should see that when we do one-var stats, right, we come up with the mean of 3.5. Right, which means that the actual population mean is 3.5. We also can see the population standard deviation is 1.7078251. So we can see that the mean of the samples is relatively close to the actual mean itself, right? So what we can write is that the mean of the means is, we can just say it's mu. I promise it might seem a little confusing right now. We're doing a lot of letters, a lot of symbols. We'll get to actual examples and it'll start to make a lot more sense. All right, standard deviation. So when we do the standard deviation of the mean, or sorry, a regular standard deviation, we see it's 1.707 such and such. When we do the standard deviation of all these means, though, we see it's 0.7, right? So that's significantly smaller, right? Do we see that? These standard deviations are significantly smaller than the population, which also makes sense, right? Because you're going to have things grouping together a lot more in the center than on the outsides, right? The original one has everything evenly distributed. But when you take the mean over and over and over and over and over again, you're going to get things a lot closer to each other. So the standard deviation is going to be a lot smaller. Yeah, so we should have a smaller one. So the formula that we can use for this is going to be you take the actual standard deviation and you divide by the square root of n. And this is basically the entire point of today's lesson. It's just that little thing. When I said earlier that this is going to be the easiest thing ever, once we get to the actual examples, like I said, right? You just got to bear with me until then. This is it. It's just this little bit. That's the only difference from this last lesson to this one. And then just for definition's sake, we call this, so this is the standard deviation of the means. Another way to say that, it's the standard error of the mean. And this whole concept is just called the central limit theorem. So if you're talking about the central limit theorem, you're saying that it's either normally distributed or the sample size is greater than or equal to 30, right? And then the mean is mu, standard deviation is sigma divided by square root of n. Okay, that was a lot. Now let's just get down to the examples, and you'll see this shouldn't be too hard. All right, so a typical computer random generator. So again, I've given you all these problems. Make sure you're going through them with me. So a typical computer random number generator yields numbers between 0 and 1 with a mean of 0.5 and a standard deviation of 0.289. So can the central limit be used? Can we do normal CDF, right? AKA, can we suppose that the sampling distribution of the mean is normal? Can we assume it's normal? So suppose the sample size is 50 and the numbers come from a uniform distribution. So what were the two things we had to do to use the central limit theorem? Either the population has to be normal or the standard deviation has to be greater than or equal to 30, right? Those are how we know. It's one of these two has to be true. Well, we see that the population is not normal. The population is uniform, so that's not great. So let's move on to the second one. Is the sample size greater than or equal to 30? Yeah, the sample size is 50. So we can use this. We can do normal CDF. We can assume that it's normal because the sample size is greater than or equal to 30, right? Or greater than 30 if you want to just say that. That's fine too. All right. Part B, suppose that the sample size is 50 is randomly generated and the numbers come from a right-skewed population. So remember, the two parts, the population has to be normal. It is not, it's right-skewed, so that's not great. The second one is that the sample size has to be greater than or equal to 30. Well, sample size is 15, so no, that's not either. So no, it is not. We cannot use the central limit theorem, right? We cannot suppose it's just normal. It's not. Let's look at the part C. So suppose that the sample size is 15, is randomly generated from from numbers that come from a normal distribution. So is the population normal? Yeah, it says it right here. So we're done. Yes, population is normal. All right, next. Suppose that the sample size of 50 is randomly generated with numbers that come from a normal distribution. So again, population is normal, so that's fine. But we also have the addition of the sample size being greater than or equal to 30. So we're good on two fronts. We only need one though, right? But yeah, both of them are true. You could say the population is normal. You could say that the sample size is greater than 30, right? Either way, 50 is greater than 30. Yeah, both work. All right. So hopefully we understand when we can use the central limit theorem, when we can assume that we're dealing with a normal distribution, right? So one of those two cases. So then here's the product, right? Here's the end result. So SAT scores are normally distributed. So we have a population of normals. So we might be using the central limit theorem. We have the ability potentially to use it. So with mean of 430 and a standard deviation of 120. So what standard deviation would you use to work this problem? So you have a sample of 35 students as randomly selected. So are we dealing with a group of people or with an individual? If it's a group of people, right, we're going to be dealing with the standard error, right, which is the standard deviation divided by the square root of n. This is for a group of people. If we're dealing with an individual, then this is just what we did from the other class, right, from the other lesson. Individual, yeah. Which would just mean that we're just using the standard deviation, right? So in the first case, we have a group of people. So we're going to use the standard deviation divided by the square root of n. Standard deviation is 120 divided by the square root of 35. And that's it. That's what I wanted to know. For a single student is randomly selected, right? So single student, we're going to use just standard deviation, regular old standard deviation. There is no n to divide by, right? A sample of 9 students. Well, hold on a second. Can we use it if it's less than 30? I thought we couldn't use this special thing if it's less than 30 students. Hopefully you remembered earlier, right? We talked about that the population was normal. So it does have the requirements, right? One of them has to be true. Since it's normal, we can do it. So it's going to be a group of students. So it's sigma divided by the square root of n. So that's 120 divided by the square root of 9. And that's all I wanted. All right. So whole reason why we're doing this lesson is this little thing right here. Basically, when you are in your calculator from now on forever, right? It was great in 7-1, not great anymore, right? That is gone forever. We are never going to do that ever again. So basically, when we do normal CDF or inverse norm into our calculator, right? We do the lower limit, we do the upper limit, we do the mu, and then we pause. And typically when I do this in a class, I yell it as loud as I can to try to jerk people awake because I want them to remember this is the easiest way to lose points, right? Especially if you don't give me any partial credit, if you don't give me any work that I can give any partial credit for, right? Because you're going to get it wrong. Either it is sigma or it's sigma divided by the square root of n. Everything else is the exact same that we did previously, right? But we just need to know now, we pause at the standard deviation. And is it standard deviation or is it standard deviation divided by the square root of n, right? So if you have an n, if we're talking about a mean, we would use that. Same with inverse norm. If we're doing that, right? That's area to the left, mu, pause. Then we either use sigma or sigma divided by the square root of n. So that is literally the only difference now. Now we just have to pause every time we do normal CDF or inverse norm. So hopefully you can see this is going to be the exact same thing that we did in chapter 7. So problem 3, the amount of snowfall centering in a mountain range is normally distributed with a mean of 86 inches and a standard deviation of 12 inches. What is the probability that a randomly selected year has an annual snow exceeding 88 inches? So normally distributed, so we're going to make our normal bell curve. 86 goes in the center. What else are we given? We're given 88.8 inches. And we want it to exceed. So that's going to be the area to the right. So probability, we're going to do normal CDF. Right? So the lower is going to be 88.8. The upper is 9999. Mu is 86. Pause! So hopefully I scared you, because hopefully you remembered, right? It's sigma or sigma divided by square root of n. So how many years are we looking at? What's our sample here? It's just 1, right? So because it's just 1, we just write 12. Just that, right? We don't have anything to divide by. So when we do normal CDF, 88.8, 9999, we end up with 0.4078. So that's our final answer, 0.4078. So the interpretation of this, right? So if 100 years were selected independently, how many would we expect to exceed 88.8 inches? Well, hopefully you see that it's 41, right? We just take our number, we multiply it by 100. So we get 40.78, blah, 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 right? That just rounds it up to 41. All right. Same problem, part B. What if we have a random sample of 36 years, right? Then what's the probability that a random sample will have a mean annual snowfall exceeding 88.8 inches? So the population mean's the same. The value we're looking at is the same, right? So this looks like it's going to be the exact same thing. We do normal CDF. The lower is 88.8. The upper is 9999. The mu is 86. Pause. Right? We're at the sigma. We got to pause. How many people are we dealing with? Are we dealing with a sample or an individual? Are we dealing with a sample this time? Right? So this time we take our sigma and divide by the square root of n. So we said our sigma was 12. Right? So we just 12 divided by the square root of 36. And you can literally just type it into your calculator just like this. And then what it spits out is 0.0808. So if, so to interpret this, so we can write 0.808 so we can see it. If 100 independent random samples of size n equals 36 years were selected from a population, we would expect 8 years, I should say years, to have a sample mean exceeding 88.8 inches, right? And again, we just multiply that by 100, we end up with 8. Good. That was it. We're done. So next problem. So a volume of the volumes of soda in quart soda bottles are normally distributed. So good, we got that normal distribution with a mean of 32.3 ounces and a standard deviation of 1.2. What is the probability that a random sample of 16 bottles have a mean less than 32 ounces? So population mean is 32.3. Our value is 32. We want less than that. So we need to figure out what this value is. So into normal CDF, our lower is negative 9999. Our upper is 32. Our mu is 32.3. And our sigma, hopefully you were yelling pause, right? Because we have to pause at sigma now. So, is it the standard deviation or the standard deviation divided by the square root of n? Well, what's our sample? Do we have a sample? Yeah, we see it's 16 this time. So we're going to do 1.2 divided by the square root of 16. And when we type all that into our calculator, what we end up with is 0.1587. So the way to interpret it, if 1,000 independent random samples of size n equals 16 bottles were selected from a population, we would expect 159, right? Again, you just multiply that by 1,000. So 159 of them we would expect to have a mean less than 32 ounces. What about if we did a random selected bottle, right? So if you notice, right, it's the exact same problem, right? It's going to be 32.3 in the middle, 32 less than. The only difference is our sigma, right? So negative 9999. Upper is 32. Mu is 32.3. Sigma, pause. We have a random bottle, right? So we don't have to worry about dividing anything. So it's just good old 1.2. When we plug that into our calculator, we should see it's 0.4013. Now, the reason why this is a difference, because remember, when we take a sample of a sample of a sample, right? When we take the mean and then the mean again and the mean again and the mean again, these might initially look the same, but in actuality, this is what an individual graph would look like, and this is what a graph would look like if it was for 16 people, right? Now, I don't need you to do that. Doing something like this is perfectly fine, right? For both of them, that's okay, right? Just a little quick sketch. But that's why we have to decrease the sample size, or the standard deviation, right? A lot more things are in the center than they are on the outside when you take the mean over and over and over again. All right. So if you got 1,000 bottles and this is your probability, how many of them will we expect to have a volume less than 32? So you multiply that by 1,000, you should get 104. Last problem, and then we'll call it a day. So a bank loan officer rates applicants for credit. The credit ratings are distributed with a mean of 200 and a standard deviation of 50. What is the probability that a randomly selected applicant has a mean rating between 200 and 225? What do we need to know to be able to do this problem? So what do we need to know to do this problem? So we have a random person, right? So to be able to do these problems like we've been doing, we have a mean, you have a standard deviation. What do we need to know? So this is coming from 7172, right? Which is all about normal. We need to know that the population is normal. Right? Because all it says is just it's distributed. It doesn't say it's normal. So let's assume this to be true. Let's assume that the population is normal so that we can do our normal distribution. So in the middle, we got 200. We want ratings between 200 and 225. So there we go. So we're going to do normal CDF. Lower is 200. Upper is 225. Mu is 200. Sigma. Pause. So how many people do we have? Do we have a group of people or do we have an individual? We just have an individual, right? So we just write our standard deviation as normal, 50. When we do that into the calculator, we see that we get 0.1915. Interpretation. So if 10 applicants are randomly selected independently, we would expect 2 of them to have ratings between 200 and 275. Again, just multiply that by 10. Part B. What is the probability that a random sample of size n equals 21 has a mean rating of 200 to 225? So again, what do we need to know to be able to do this problem? Well, we have a sample, so let's remember, we said either the sample could be greater than or equal to 30. Is it? No, it's 21. Or what's the other thing that we said we could have? AKA, what do we need to know to be able to do this problem? We need to know that the population now is normal. So let's assume the population is normal so that way we can do this problem. So since it's normal, right? Mean goes in the center of 200. We want to know between 200 and 275. So we do normal CDF. Lower is 200. Upper is 275. Mu is 200. Pause. So, how many people do we have? Is it an individual or is it a group? We got a group, right? So we got to take our standard deviation and divide it by the square root of that. So it'd be 50 divided by the square root of 21. And when we're done there, we end up with 0.4890. Which means that if we have 1,000 people, how many of them would we expect to have a mean rating of this between these two numbers? 489. Last part, and we're done. So if a probability has a random sample of size 48, what's the probability that the mean rating is between 200 and 275? So what do we need to know to be able to do this problem? Actually, this time, we don't need to know anything. We can do this problem, right? Because remember, we said we can do it if n is greater than or equal to 30. It is. So we're good. We don't actually need to know anything. We don't have to assume anything. We can just go ahead and do it. So right in the center, we got 200, 275. This is looking super familiar, right? We do normal CDF. Lower is 200. Upper is 275. Mu is 200. Pause. So sigma, right? We do have an n. So we're going to take our sigma and divide it by the square root of 48. Because we have 48 people. And when we do that, we end up with 0.4997. So interpretation, if we have 100 people, we should end up with half of them, 50, having a mean between 200 and 275. Just multiply that by 100. All right. Hopefully you kept with me and you see that this is very similar to just the chapter 7 stuff, right? The previous stuff that we talked about with normal distributions. All right. If you have any questions, definitely let me know.